Good evening, everyone. My name is Yves Goeleven. I'm presenter for today together with Sean Feldman. We are both solution architects working for a particular software, and we're also Azure MVPs. And we're hosting a dual webinar, which is targeted at Azure Service Bus usage. In this first session, we will be discussing how to use Azure Service Bus SDK natively, try to give you a solid understanding of what the service itself does, how you use it, and as well what the challenges are, which things we ran into over the years of using it. And then next session, it will be more about End Service Bus itself, the explicit choices that we made there, for using Azure Service Bus. So if you have specific questions, please find the Q&A section in your Zoom launch bar. You can ask questions there. We will have a Q&A section at the end of the webinar, so where we can answer them. If there are a lot of questions, we will try to answer them in the Q&A section already, just to save a little bit of time. All right, let's get started. So, when do you need Azure Service Bus? So what is it for? Well, Azure Service Bus is a online communication service which has the specific capability that it can make software components talk to each other by using outbound connections only. So it's extremely useful when you have different software components that need to be able to talk to each other, but the network boundaries are preventing you to do so. And this happens quite a lot. So if you ever ran into Windows Azure itself, you know that certain cloud services have their network configured in such a way that they cannot talk directly to each other. Or maybe you may have multiple on-premises data centers which have firewalls in between, or you have different branch offices all across the globe. You have hybrid solutions that are either partly on-premises or in the cloud, or you may have solutions where there is software that you don't even know where they are. And this happens in the case of IoT and mobile devices. So in all of these scenarios, Azure Service Bus is a great technology to allow these software components to talk to each other. Now, in order to do that, the Azure Service Bus service itself has an internal architecture which is geared towards it. So if you look at the diagram in front of you, you see a client which is making an outbound connection to the service. And it's doing this primarily through the DNS system, which is a resolution of your namespace of servicebus.windows.net towards a specific IP address that targets the load balancer of a specific installation of Service Bus. We call this scale unit. Inside the scale unit, the first thing that your request or your connection will go to is a load balancer. This one provides high availability between the different nodes inside the service. Then the service itself consists of two layers of nodes. And the first layer is what we call the gateway node. This is the one that you actually make your connection to. So a gateway node will accept your connection, and it has the responsibility to perform authorization, whether or not you're allowed to make the connection. And it's also responsible to look up inside the system where a certain entity is hosted. This entity is hosted by something called a broker node. That's the node that's actually performing all the operations. So if you send a message or receive a message, it's actually the broker that's performing the operations on the entity store. This entity store, it depends a little bit on the type of namespace that you're using, but it's either a SQL Azure database or it's a storage container. This is important to know because it's quite a heavy setup for individual queues and topics. Now I use the term entity. This is something, a generic term that we often use when we're talking about anything that is hosted inside an Azure Service Bus namespace. Now for the scope of this presentation, we will only talk about queues, topics, subscriptions, and rules. So each of these is an entity. So each of these is stored in a SQL Azure database. But there are many other entities, like relays, event hubs, consumer groups, IoT hubs, etc. It's all the same infrastructure. But for now, we will just focus on queues, topics, subscriptions, and rules. A queue, I assume you know what a queue is. It is a construct on which clients can send messages to and other clients can receive from, but only one gets the message. In a topic, you can have multiple clients subscribing to this entity, and they will all receive a message sent by the sending client. All right. The first set of topics that we will address is connectivity. Connectivity, you will connect to the broker for two major reasons. The first reason is that you want to create or manage the entities that are hosted inside the service bus. You typically do that using a Namespace Manager. And the second reason that you want to connect to the broker is to send and receive messages from these entities. And that is typically done through the messaging factory. I will show you both how to use it and what you need to keep in mind while you're using them. So the Namespace Manager is the SDK class which allows you to manage the namespace or the entities inside the namespace. In order to do so, you need to provide two different things. One is an address which allows the DNS system to resolve the scale unit for you so that it knows where to create the entities. And the other one is a token provider. Typically, this is a token created from your connection string, but you have many different options. The token provided by the token provider will be used on the gateway node in order to authorize you. Now, the operations that you can perform with the Namespace Manager are typical CRUD operations like get, exist, create, update, delete, etc. The easiest way to do this is using the Namespace Manager itself as a class, but you can also do this through a REST API and even through the RM system. You can perform the same operations. Now, each of these connections are single shot. So the Namespace Manager will perform an HTTPS request to the REST API to perform one of these operations. What is important to realize here is that every entity is backed by a SQL database or an Azure Blob storage blob. So creation is probably pretty expensive if it needs to spin up SQL Azure databases. That's something that you have to keep in mind at all times. So don't go and drop, delete hundreds of queues and topics for testing purposes, for example. Don't do this over and over and over again. It's very expensive. So set things up once and then reuse the resources that you created. I have a little C# code snippet that I wanted you to show. It shows how you actually go by and create a specific entity. So this is very basic code. In the SDK, you will find a class called Namespace Manager. You can use this Namespace Manager to check if a certain entity exists, or you could create a new entity if it doesn't yet. But before you can do that, you must authenticate to the gateway at a specific address. So the specific address is constructed from your namespace. You can find this one in the portal, in the Azure portal. And you have to turn that namespace into something called a Service Bus URI. It's a very useful helper method that allows you to do that. And next to the address, you also have to provide your credentials, your token. Now in this case, I'm using a managed shared access signature and a managed key. There are other options which you can choose from. It just depends on what you're using. Now, once you have the connection to the Namespace Manager, you can create a queue description, you give the name, you can set some properties, and then you can ask the queue or the Namespace Manager to create it. I'm going to run this one quickly so that my system is set up. So it probably doesn't exist. Now it created it. You see that it took quite a few seconds, so it's an expensive operation. All right, so now that we have the basics covered, let's have a look at what we need to keep in mind when we are performing these operations, because a lot of things can go wrong during the execution of these methods. And the things that you will have to deal with are timeouts in your local network. You may have timeouts in the Azure Edge network. You may have timeouts at the DNS level. You can get all kinds of timeouts. And if your call gets through, which usually is the case, you will also have to authorize at the gateway. And at that point, you can also get an unauthorized exception that you need to deal with. Any token that you provide through the token provider must have a managed claim, otherwise you will not be able to use the Namespace Manager. Now, if you get in, you can also get some exceptions from the broker. There are two kinds of exceptions that can come back. A frequent one is what's called a transient exception. A transient exception is an exception that occurs right now, but will probably not occur in several seconds or in a minute or so. So that's an exception that the broker says, well, yes, I'm sorry, no, I cannot help you right now, but I may help you in a few minutes. So just back off, retry at that point. There's no real harm or damage done at the broker side. Now, if you have non-transient exception, that means something is really gone bad, and you need to be able to deal or at least stop processing at that point. And another common source of problems is that multiple clients will be connecting to the broker at the same time and trying to execute the same operation. This is typical when you have multiple client processes that are starting up and they all want to create the same queue or the same topic. That's something you also have to deal with in your code, is that you have to handle concurrency conflicts properly. Now let me show you a little code snippet that demonstrates this. So the code is roughly the same, but the only difference is that the queue exists and create queue methods are wrapped in a try catch. So here I show different strategies that you should use in order to deal with these different types of exceptions. So the first one is you're not allowed to access the gateway, or you're not allowed to access the entity. And in that case, you have to abort. There's nothing you can do about this. There's no way to recover. The claim that you are using to authenticate to the gateway is not allowed to perform the operations. If you get a timeout exception during these operations, you don't really know what happened. The timeout might be local, timeout might be caused inside the broker. It might be caused after the entity has been created or before. You just don't know. So in this case, the queue that you try to create may exist or may not exist. And the best strategy to deal with this kind of exception is to check whether or not the entity existed already. And if not, just retry the operation. Right? Don't do this over and over and over, because you will quickly get an infinite loop if you try to do that. If you have concurrency problems, then you will get a messaging entity already exists exception. This is usually okay, because it means that another instance is trying to perform the same operation as this one. And then finally we get the messaging exception. This indicates problems inside the broker. So you can validate whether this exception is transient. If so, then retry is probably the best way to deal with it. But do bake in some backup mechanism. So wait a few seconds, do a thread sleep or something, and then try later again. If it's not a transient exception, then something is really bad, and you best abort and investigate manually. So those are the connectivity problems that you have to deal with for every single operation that you perform against the broker. So timeouts, access control, concurrency conflicts, and problems from inside the broker. All right. Now, the second way to connect to the broker is by means of the messaging factory. And the messaging factory is intended to send and receive messages. You create this one in a very similar way than Namespace Manager. You also have to provide the namespace address, and you also have to provide a token provider. The connection settings that you can provide here is to control how the messaging factory is establishing the connection behind the scenes. Because this is something very important to realize from the architecture, is that the physical connection, the physical network connection, is maintained by the messaging factory. So this is something that took me a long time to realize, because when you're coding, you're usually coding against the message sender or the message receiver. You create those entities from the factory, but they don't own an individual connection. It is the messaging factory that has the physical TCP or WebSocket connection behind the scenes with the broker. Now, when you create a message sender or a receiver, this one will establish a logical protocol level connection. So there is still some handshaking going on, but it's more to determine whether or not we will use AMQP or SBMP as a protocol. It doesn't set up the physical connection behind the scenes. Establishing a physical connection is also something very expensive. You don't want to do this over and over and over again. And it's also very important to think about when you're doing performance tuning, because one physical connection will only get you so far when it comes to message throughput. If you want to increase your throughput, you should increase the number of messaging factories, because that's what gives you the most benefit as you get a new connection, maybe even to a different gateway node. Let me show you quick code sample again, how you do this. So controlling creating the messaging factory is done by a create async method. And again, you need to provide two different things. One is the URI. This is the same as the one that you had to provide for the namespace manager. And another object is something called the messaging factory settings. And here you have to provide, again, your token provider so that you can authenticate, but you can also make other settings. Like in this case, I gave the instruction to use the SBMP protocol for communication between the senders and the receivers. The choice between TCP and HTTP is something that you don't make at the factory level, but you have to do it before you create your first factory. And you do that by setting the service bus environment system connectivity mode. I'm going for TCP, but you also have the option here to use HTTPS, which behind the scenes is creating a WebSockets connection over port 443. So I think that's one of the questions that Bertus van Dalen is asking. So this is the way to actually do that. Now, once you have a factory object, you can use the factory to create a sender and the receiver. But do note that at this point, both the sender and the receiver are using the same data connection behind the scene, or the same TCP connection behind the scenes. They are sharing it. Right? If you want to have an individual connection for this sender and this receiver, then you will have to create an individual factory from which you create the sender and the receiver. Once you have sender, it's very simple. You can start sending messages using send async, and you can receive a message using receive async. We'll come back to these methods a little later. Let me run this guy to see if it's actually working. So it has sent and received the message with a body called some data. Oh, that's working fine. All right. So besides all the things that you had to keep in mind when establishing a connection with the namespace manager, you have to take care of a few more things in this case, because messaging factories are creating a long-lived connection. So you want to have the ability to receive and send messages as long as your application lives. This is not something that you want to do once. You want to do it for days on end. And there are problems that will occur during that lifetime of your application. You will have local network interruptions. There may be hardware failures, both local and in the cloud. And the gateways where you're connected to, they will have to reboot every now and then as well in order to get software updates. So your physical connection will drop. But on the other hand, establishing this connection is also very expensive. So you don't want to do it over and over and over again for every time you're going to send a message. So what you need to do in this case is to actively manage the life cycle of your factories, right? Especially your factories. So you need to maintain the instances that you created before. Look at the state of that connection, and if it closes, you will have to create a new factory to reopen the connection. So again, I have a small code sample which will show you how to do that, if my Zoom bar doesn't get in the way. So in this case, we have the same setup code, created the sender and the receiver, but what is important is that I have a static variable at this point to maintain my factory. It's static, I know that's not the best practice, but we'll go for it anyway. And whenever we created a receiver or a sender and we want to use it, we always should check if it's closed or not. If it is closed, we need to create a new one. I'll show you the method here below. So if it is closed, we need to create a new one. But before we do, we need to make sure that the connection that we're using, the factory, is also still valid. So I have a helper method which is called ensure connection. And in this connection, I'm going to check if the factory is null or if it's closed. And if either of these cases occurs, I will re-establish the connection. But this code is exactly the same as in the previous sample, but this time I'm doing it over and over and over again. Check if it's closed, and if so, recreate the factory. This is effective instance level management, and you need to do it on every single operation that you want to execute against it. So in order to demonstrate this, I've put this receive code, the send receive code, inside a while loop. And as long as I just don't hit X, I will continue to send and receive a message. But if I hit C, I will close the factory manually. So now I'm doing it manually. In reality, of course, this happens because of the drop of connection in your network, or the gateway that you connected to is going to reboot. So let's give this one a go. So what we now see is initially it created a new factory, it created a receiver, it created a sender, and it receives a message with a body called some data. Now if I hit enter, it's going to do the same thing. It's going to reuse the same sender and receiver. The factory is still open, so it could send and receive some data. When I hit C, it's going to close the factory, so it's going to close the connection. And then I have to re-establish everything again. So the factory is closed. The senders and receivers will automatically be closed as well because they're sharing a TCP connection behind the scenes. So I have to create a new sender, I have to create a new receiver, and I also have to create a new factory in order to create them. Once this is done, I can happily send and receive messages again, right? So this is something that you have to do in your code. At all times that you want to use a sender or a receiver, you have to check if the connection is still there, and if not, re-establish it. All right. So for receiving, I have a little section about issues that you may run into while you're actually performing a receive. So there are two ways to perform a receive. One is called receive and delete, and the other one is called peak lock. These are different mechanisms. Receive and delete basically means that at the point that a message receiver is pulling a message from a queue or an entity, it immediately deletes it. So this gives you single shot processing. So you process it once. If it succeeds, fine. If an exception occurs, fine as well. Right? You lost the message at that point. There is no option to try again. We actually advise against this mode for the majority of applications, because the majority of applications are more workflow style and they require higher reliability typically. And because the cloud is an environment where transient exceptions are very common in all services, you will get exceptions. There's no way you can prevent them. So for typical applications, we advise against receive and delete. So we'll go quickly back to my code again. So receive and delete is a setting that you can pass in. It's called receive mode. When you create a receiver, I can find my code. So when you create a receiver, you call the factory, you say create message receiver async, and one of the options that you can provide is the receive mode. Now in this scenario, I want to show you that you actually lose the message. So we're going to send the message initially with some data in it. Then we're going to receive the message, and then we're going to throw an exception. Then we're going to hit a key to try receive the message again, but you will see that there is no message to receive anymore. It's gone. So let me run the sample again. No, it should be selected. So let me run the sample. You can see that it actually created receiver and sender. It has sent a message, and then an exception got handled. Now if I hit a key to retry, I'm going to see a message that there is no message on the queue anymore. The message is gone. So you see, no message received. So we have processed the message, but an exception occurred, and then we lost the message. This is not an ideal mode for the majority of applications. All right, a better way is to use peak lock. Peak lock is a mechanism in which the receiver will not delete a message when it pulls it from the queue, but it will apply a lock to it. Then it starts processing, and after processing it will perform an explicit delete operation, which is called complete. Or if something went wrong, it can explicitly call abandon, so that the message reappears on the queue. This gives you multi-shot processing. Basically you can try, but if something goes wrong, you can retry, because either the lock will disappear on its own because it's temporal, or because you explicitly abandoned the message, you can retry it, or it will be retried faster. The service bus is maintaining a retry counter at the broker side as well. And if that counter is exceeded, it will safely store the message on another queue, which is called the dead letter queue. So no matter how often things go wrong, you never lose your message. It's always available for processing. Now there is one gotcha with this method, and that is if the processing time is slower than the time allowed to keep the temporal lock, then the message will automatically reappear and it will be processed again. So you may be processing the same message twice. That's something that you have to keep in mind. Right, let me give you another code sample, what this looks like. So in this case, the code to create the receiver is exactly the same, but we passed in a receive mode called peak lock. Now in this first variation of the demo, I'm going to send a message as well, then try to receive it. Sorry, here, try to receive it. And again, we will throw an exception. And this is exactly the same operation as before, but because we have the peak lock mode, you will see that the operation is executed a few times. To save some time in a demo, I have reduced the number of times that we try, but it should still give it should give you the ID. So we received a message with ID 3FF something, and an exception has been handled. Now we will hit it again, and you see that we are handling it again. Let me hit again, and here it is. Now I'm so slow in clicking, but it actually it takes a while. It's because I've set my receive time to 5 seconds that it looks fast. But the default receive time and the default lock time is 60 seconds, so you have a minute between each operation. It takes quite a while. If you want to speed this up while still retaining the default locks, you can explicitly abandon the message, or when it succeeds, you can explicitly complete the message. So in this case, it should go faster. Now I probably cannot do it so fast that you see the difference, but let me give it a try anyway. Yeah, you see I hit enter in succession twice, so it took less than 5 seconds to actually handle the retries. It still took 5 seconds to notice that there is no more message though. But that's the difference, right? So now we have retry built into our code, and it's going to execute a lot more reliably. All right. Now, it's not just how you receive it. It's also how you decide how you deal with multiple messages, because most applications will have multiple message types being exchanged by the different software components inside of it. The first thing that you need to consider is something that we decided to call a topology, is how are you going to lay out the entities in your service bus namespace in order to fulfill your business goals. A few very common approaches are queue per message type and queue per receive. This basically means that you assume that one queue will always have messages of the same type, or you mix them by target, and this is the second mode. Now there are several other topologies that you can use, and we will talk a lot more about this in the next webinar, but it's something that you have to keep in mind. The second thing, which actually got me fairly hard during the development of N-Service Bus, is serialization challenges. So the service bus itself is also doing internal serialization, but it's not doing it all the time. So you have to watch out how you do it. And you need to deserialize your messages in exactly the same way. And this is just the internal serialization. If you have serialization of your own, let's say JSON serialization, you will have to additionally look at what the data type is inside the body format. I will give you a code sample about this in a second. And then finally, there is also concurrency that you need to keep into account. If you, for example, put multiple receivers on a single entity, then multiple code paths will get messages at the same time. But if you have pieces of code that are shared between these different code paths, you have to ensure that all of this code is thread safe, right? And you don't even need to have multi-threading in there. Because we live in an async world today where all async methods are allowed to interleave with one another, you can actually have concurrency problems even if you're single-threaded. I want to go back to the serialization challenges because this is a major gotcha that happened to my code in the past. So let me show you this sample. I'm going to send some data in 3 different ways. The first sender is going to say send a new brokered message, and it's going to pass in a string. Imagine that this string is a JSON serialized object. In the second method, I'm going to first convert this string into a byte array, and then I'm going to send the byte array. And in the third method, I'm going to first convert the string into a byte array and then into a stream. Now let's have a look at what's going to happen. Let me run the sample. All right, so we have set or sent the message. I'm connected to this namespace, and I should see in my queue, I should see 3 messages in the receive part. Let's have a look at these messages. So they contain roughly the same data, right? And if we look at these messages, we will see that the data is visible as well. This one says some data 1, this says some data 3, this says some data 2. And at first sight, it looks like there is no difference. There are no different headers, so there is no data that seems to be off, except for one thing, and that's the size. If you see that the size of the third one, so the one that we have first converted to a byte array and then passed as a stream, is a lot smaller than the other 2. And what's going on here behind the scenes is the internal serialization that Azure Service Bus SDK is performing. So if you look at the documentation of the brokered message, you will see that it has multiple constructors. And one of these constructors accepts an object and the other one accepts a stream. And the stream constructor is actually not performing any serialization on the data, while the object constructor used in this case is. So what's happening here behind the scenes is, even though you're passing in some valid JSON, is that it's still turning the data into a binary serialized object, a .NET specific object. So it's not only bigger, but it's only not going to be readable by any client other than a .NET client. Now, there's a second problem here, is that this tool, Service Bus Explorer, is actually so smart that it would automatically deserialize both versions. So you don't notice that you're doing anything wrong here, because it looks like both versions are actually working. Until after a few years, somebody tells you that your product is not working when you have a Java client or something. So that's something that tripped me up quite heavily. All right. So finally, for my part of the webinar, I wanted to discuss in the processing, and you're using Peak Lock, then the messages will eventually end up in this thing called the letter queue. This happens when the max delivery count setting is exceeded. So this is the retry count that I talked about a few minutes ago. But there are a few challenges with this as well. So the messages that are actually ending up in this dead letter count, you don't really know why they ended up there. Did they end up there because they are poisonous, because, for example, they are corrupted, their body is corrupted? Or is this just because of a business exception that needs to be handled? Secondly, this retry mechanism, it might cause problems downstream. So when you're, for example, using a third-party web service, can it actually handle this scenario where we retry things 10 times and then maybe again when we resubmit from the dead letter queue? And finally, another problem that you will have with this is that each entity has its own dead letter queue. So it becomes quite a challenge to actually start monitoring all of the entities in your namespace. I can demonstrate this with my final code snippet, and then I will give the tag to Sean. And in this sample, we will be processing, we will be sending a message once, and then we will be tracking the processing attempts. So we are going to receive this message, and as long as we receive something, we are going to print it out. So the default retry max delivery count set on the queue is 10. So we should see that it's actually executed 10 times and then ends up on the that letter queue. I accidentally closed my so let me clear that letter queue first, because I had some from the previous run. All right. So what you should see now is that the code is actually performing 10 attempts, and then in the end it will push the message to the dead letter queue section. So we're going to run it. We see that the message is processed 10 times. That's the default counter, and then nothing happens anymore. So now we would we can look into the queue, and we see that there is one message on the dead letter part of the queue. Now we're going to receive it, and you can put it back. You can resubmit it to the queue if you want to. But this is the dead letter queue mechanism, and the challenges that you can have with it. So I'm now going to give the word to Sean, who's going to talk you through the sending part and as well as some performance tips.
Right. At this part, we'll look into sending messages and some of the challenges associated with it. Just to sum it up, the things that we'll look into are going to be throttling or how we get throttled when we're trying to send messages out. The message size and its importance when we're trying to send one or more messages, situations that we can end up in, such as flooding entities, and we'll look into something that is well known as transaction and learn what transaction with Azure Service Bus actually means. So we've looked before with Yves how to handle different exceptions that may be raised by Azure Service Bus. And there are certain exceptions that need to be taken care of in the user code. One of those good examples is server busy exception, which would normally happen when we're trying to send a message and we're getting throttled down. Usually, the way we would handle this code is we would have to decide whether we retry again until we're successful, or after a certain number of failed retries without any success, we would throw an exception declaring that we're giving up. You have to take into consideration the obvious thing that retries can fail, and we have to, on top of the retries that we would perform, there's also built-in retries that Azure Service Bus native client is providing out of the box. So this would be in addition to what Azure Service Bus is doing natively. And the best recommendation is whenever we get throttled and we receive server busy exception, to wait at least 10 seconds before trying that again. Let's have a look at the code, which demonstrate such a situation. Now, it's extremely difficult to mimic such an exception. So what we will do is I'll just demonstrate the code that is supposed to handle the situation when we get throttled. On line 33, you will see that rather than just sending a message in a conventional way, what we do is we invoke send with retries async. It's an extension method defined in line 57. And briefly looking at the parameters, we have an action to take. We have an action to take when retry should take place. We're taking a time span, which indicates the interval to wait between the retries and maximum number of retries that we are going to allow. For internal usage of the method itself, we'll have an internal counter number of retries that we have attempted so far. Looking at the invocation of the method at line 33, you'll see that the initial action is just sending the message itself. The retry action is to actually send a clone of the message, and that's because once a message has been attempted to be sent to the broker, it cannot be reused again, and you have to create a new clone in order to resubmit it. We'll retry after 10 seconds, up to 5 times. So if after 5 times we're not successful, we'll throw an exception. The extension method is basically looking at used retries. If we haven't been in this method before, if we haven't retried this send, then we'll take the original action. Otherwise, the action to take will be always the send with the clone, which we will attempt. We'll catch the server busy exception. That's basically the throttling performed by the broker. If number of attempts that we have tried so far is less than the maximum, we will go again into retrying. Otherwise, we'll just rethrow the exception as is. And if we still can retry, we'll wait whatever the period of time that was defined for us. By default, should be 10 seconds. And we will retry again, passing all the arguments except the retry count, which we have already covered. Message size is another thing to keep in mind, especially when we're sending messages. As long as message size has a maximum limit that can be used for standard tier, it's 256 kilobytes. For a premium tier, it's significantly bigger, up to 1 megabyte, where headers take 64 kilobytes regardless of the tier, and which means that in standard tier, it's less than 200K for a message. As long as the message is smaller than the maximum size, the broker will accept it. The message will be sent successfully. Otherwise, the message will fail with an exception message size exceeded. You have to keep in mind one caveat, which is the size of the message provided by the property on the brokered message is not necessarily the final size of the message. The message has to be serialized in order to determine the final size. So there's a little bit of overhead. Unfortunately, the size of the message is not known until it's actually sent out. The best effort that can be done is some sort of estimate to add certain percentage on the size that can be derived from the brokered message property. Another example of a situation that needs to be taken into consideration with sending is overflooding entities. As an example, we take a subscription. So here we have a scenario where we have 3 different subscriptions on a topic, and one of the subscriptions is not monitored. What can happen is that a subscription that is receiving messages and is not monitored can eventually overflood by receiving messages and exceeding the maximum size. The challenges associated with that, aside from overflooding the entity itself, is actually the overall performance, degradation of the overall performance of the namespace, and obviously potential outage that can happen. A possible solution that can take place is, rather than monitoring individual subscriptions and having receiving clients associated with the subscriptions, to actually forward all of the messages to a single entity, such as queue, for example, or another topic that is ensured to be monitored and have a receiving client and can scale out or in based on number of messages on the load that we get. Now, another gotcha to keep in mind is that even if subscription has a time to leave defined on it, it doesn't necessarily mean that the messages will be removed, because with Azure Service Bus, the broker actually removes the messages that have TTL expired once messages are attempted to be received. The next feature, which is a great feature on Azure Service Bus when sending messages, is transactions. And transactions allow us to have messages sent successfully or fail as an atomic operation. In other words, either all of the messages are sent or the messages are going to fail as a group. Now, it's not entirely the transaction that you might have in mind. It's only focused on a single queue. In other words, we cannot send to multiple destinations. It has to be a single destination. We'll look into how to potentially overcome this problem in a later slide. And you cannot involve other transactional resources in Azure Service Bus transaction. It's solely for the transport, solely for the messages. Let's look at a sample code. So here we have, in our example, 3 messages, first, second, third. And what we will do is we'll attempt to send those messages inside transaction scope. If I run the sample, you will see that all of the messages were sent successfully. Now, if looking at the namespace, at the queues, we should be able to receive the messages, and we received all 3 of them. So if I would put a pause and look at the debugger, look at the code as we execute it, we would see all 3 of the messages appearing on the queue. And then as we receive the messages, all of them removed from the queue. Now, one of the issues with the transaction or transaction scope used with sending multiple messages, even to the same destination, is that we cannot involve any other destination. The commented out code that I have here is basically indicating that by trying to send a message to another queue, the moment we will attempt something like this, our transaction scope will throw an exception. Because we're involving more than a single destination. And here we go. We were trying to span multiple entities. So just keep in mind that transaction, when you're sending out, transaction is great when you have messages destined for a single queue or a single entity, I should say. Whenever you need to involve multiple entities, just transactional scope is not going to work. There is another side to the transactions, is that number of messages is actually limited. We can only send up to 100 messages within a single transaction. The moment we exceed number of messages, we will receive an exception indicating so. The sample that we have here is, here we go. We'll just construct 101 messages, trying to send all of these messages and completing the transaction. Transaction will not be completed. Messages will not be sent. And we'll get an exception indicating that we're making an attempt to send more than 100 messages in a single transaction. Now, what happens if we have transactions with receive operation? Again, in case of a single entity, this scenario would work. We would be able to receive an incoming message, send out to the same queue other messages, and complete the transaction scope. But the moment we're trying to either the moment we're trying to send and receive to multiple entities, just like in this sample, receiving from queue A and sending to queue B, or sending to queue B and one of the messages to queue A, the transaction will fail. Also, you have to keep in mind that the definition of transaction is slightly different from what we traditionally have in mind. The abandon of incoming message cannot be included in the transaction, only the completion. And again, we cannot utilize multiple transactional resources. Now, in order to overcome this somewhat limitation, Azure Service Bus Transport provides an additional feature called Send Via, or let's look at how it actually works. Defining the scenario is following. The incoming message that we will be processing will be coming from originating queue, my queue. Once we receive that message, we're going to process it. As a result of processing, we might decide that we need to send messages to queues A and queue B. What will happen is actually the following thing. The message arriving to the receiving client and receiving client intending to send messages to the queue A and queue B. Behind the scenes, the messages are actually dispatched to the my queue by Azure Service Bus, where my queue is used as a transfer queue. Once transaction scope is completed, successfully completed, the incoming message is completed and transaction scope is completed as well, Azure Service Bus is going to forward the stored temporarily messages for queues A and B to their actual destination. So it would appear as we have received the message, processed it, and messages destined for queue A and B were sent to A and B if operation is successful. In case we have an exception, we would have to abort the operation, would have to roll back our transaction, and in that case, the original incoming message would appear again on the input queue, on my queue, and the messages that were sent out as a result of processing to the queues QA and QB will be reverted, and they will never get to the queues. Let's have a look at the code that will demonstrate this. So 3 queues that we're talking about. My queue, which is used as an input queue. and two destination queues, QA and QB. We will create a message, which is the original message to kick off the process. This is the incoming message, sending that message out and receiving the message to mimic the whole process. Once we have the incoming received message, we'll start a transaction scope. Within the transaction scope, we're sending two messages to two different queues, to the QA and to the QB. Once we send out those messages, they are stored on the original incoming queue. We will mark the received message as completed and complete the transaction. That will kick off the transfer. The original incoming message, the received message, will disappear because it will be processed, and QA and QB will include the two messages that we would want to, we intended to have as destination messages. If we run this code and look at our entities, here's my queue at the end of execution. You'll notice that the incoming message is gone. QA and QB, each one of them will contain the messages that we originally sent. Message for QA and message for QB in the second one. Now, this was a successful transaction. What happens if transaction is unsuccessful? In that case, what we need to do is we need to catch the exception and abandon the message. The reason why we abandon the message is the same reason that Yves has mentioned before, to make the message appear faster on the input queue. For example, we could somewhere here throw an exception, emulating processing going really bad. So at this point, we have gone through receiving the message, sending out to QA and QB the message, throwing an exception, and basically rolling back. Let's look at the queues that we have at this point. You will see that my queue has the original message, the message that we've processed already. We can look at the delivery count. You'll see that it has been increased to 2, indication that we have processed the message already once, and QA and QB are empty, containing no messages. In other words, we reverted those messages. And looking at this feature, this is an extremely powerful one because that actually gives us a transaction. Keep in mind, transaction on the messages level only, not for any other transactional resources. Now let's briefly look at the performance. A few things that I'd like to highlight, the do's and the don'ts about factories, about batching, coding practices, and prefetching. So as Yves pointed out, factories are in essence connections with the broker, and using multiple senders definitely helps, but all the senders depend on the message factories that created those senders. Therefore, more factories obviously helps, rather than having multiple senders associated with the same factory. Having one-to-one will one message sender associated with one messaging factory will give you a higher performance. Let's look at the code sample. So in this example, we're going to send 100,000 messages. We'll use 16 senders, and when we create the senders, we basically have a Boolean flag which indicates either creation of a sender with a single factory. In other words, all the senders are associated with a single factory, or each sender will have its own dedicated factory. There are a couple of other things that we do here. I'll go over this in details in the next slide, especially how we perform the send operation rather than just awaiting for the send async. we collecting the tasks and execute them all together. Let's run this. Oh, sorry. Let's run the code and see how long will it take us to send 100,000 messages. Now, you have to keep in mind that it also depends on multiple factors, such as your connectivity to the data center, that specific region, if you have noisy neighbors or not, and some other performance parameters. In our case, it took about 6 seconds. Now, if I'm going to create all of our senders of the same factory, you will see that instead of 6 seconds, it's going to take drastically more time. And the reason for that is because all of our senders are going through the same connection established to the broker. So in essence, we have a certain size of a pipe, and we're trying to push all of our messages through the same pipe rather than having several pipes. So this operation, based on previous runs, probably can take up to 30 seconds. Here we go, 25 seconds. The next one is batching. Obviously, sending multiple messages in a batch is going to guarantee better performance. There's two kinds of batching that you can easily control. One is the batch flush interval, which is basically grouping messages. What will happen is the native Azure Service Bus client will group the messages before sending them off to the broker. Now, I have to mention that if you have very low throughput and you desire low latency, probably having that kind of batching enabled doesn't make sense. You would want to disable it. You basically have your single message dispatched immediately right away. The second kind of batching is the batch sends, when you grouping your send operations together and invoke as a single task, await for that single operation. Now, there is, again, same concept of the maximum size, just like for a single message, so is with the batch. The batch cannot exceed maximum size of a single message, i.e. 256K for a standard tier or 1 megabyte for a premium tier. The moment we exceed the size, we'll get an exception. Now, as you remember, the bonus of not knowing the actual total message size, so if you just collect your brokered messages before you send and sum up the size property, it might not necessarily give you the accurate size, so you have to sort of estimate it a little bit. And the extra bonus that we get is same thing as with transactions. We cannot send more than 100 messages in a single batch. Therefore, if you have a process that sends out messages and you're trying to optimize performance by batching them, you have to ensure not only that the size is less than the maximum, but also that the number of messages is less than 100. Now, if we go back to the code that we used, one of the good coding practices, as I said, is rather than having multiple messages sent one by one and awaiting for completion of the sending operation, it is much better to take advantage of the async nature of the Azure Service Bus client, group all the send tasks, all the send operations, and then await for the whole group of these tasks. This significantly improves your performance. Now, the last but not the least is prefetching. When we receiving messages, usually the samples that you've seen so far, we were receiving a single message at a time, which means that every receive requires going a round trip to the broker to fetch another message. Azure Service Bus allows defining prefetching, which means rather than receiving a single message, we receive a certain amount of prefetched cached messages. Those messages are loaded when we receive the originally requested message. Those messages are getting locked on the broker, which means they're subject to lock duration, like any other one, which is by default 60 seconds. Each client, each message receiver will maintain its own in-memory cache, which it will utilize. This will probably affect the very first receive, the very first message received, but all the subsequent message receives will be extremely fast because messages are coming from that in-memory cache. Now, a few things to keep in mind that prefetched messages, we cannot control the renew locks. So if you have been receiving the first message for a very long time, all of the prefetched messages will be unlocked on the broker and will be available to other competing consumers, which means that prefetch size heavily depends on the processing code and how fast you execute that, which means that it's a delicate balancing between speed of processing and the size of your prefetch. Keep in mind that prefetched messages are not evicted from the cache. There is no connection between the fact that message was unlocked on the broker and the message sitting in the in-memory cache. Therefore, the messages will be processed and they will fail when we'll try to complete those later. The other thing to keep in mind is what happens with the messages that have TTL, prefetched messages that have time to leave. They're not evicted from the cache. The broker, when sending messages as part of the prefetch, is evaluating time to leave at that moment. If messages are still valid, they are prefetched, and the client, the message receiver, will not reevaluate TTL. It will try to attempt the messages, and those will fail when we'll try to complete them. Let's have a quick look at the prefetch code. The big difference is that the prefetching is defined on the receiver level. In our scenario, I'm specifying 256 messages to fetch. This is because our processing is actually minimal. If we look at the code, so we have 16 receivers with 16 associated message factories, which means we're supposed to receive it quite fast. Every second we'll output how many messages per second we received. And the way we receive it is, rather than using conventional receive message, we'll use a construct on message API provided by Azure Service Bus native client, which allows to register in a simple way an asynchronous callback. What we're doing is, this whole operation is basically, give me 1 second here, we're not doing anything with the message itself other than incrementing our account to be able to perform the, to output the number of messages per second that we receive. As part of the onMessage API, we provide the options, which is auto-completion. So I'm cheating here a little bit. Basically, the Azure Service Bus native client will complete messages for me, and number of concurrent executions or number of callbacks that we're going to have, in this case, just one. So let's run this example, and you will see the previous sample when we sent 100,000 messages, we seeded our queue. In this case, we're receiving the messages, and you can see that we get processing of over 20,000 messages per second. Again, don't necessarily look at this number as an absolute number that you're going to get. It can vary, and we're not using premium tier for this. Therefore, performance is not promised to be consistent as it is with the premium tier. At this point in time, we've exhausted all the messages. There is no more messages in the queue, and we're just waiting for the completion. So this was prefetching. So after looking at all of this, Service Bus is a great service with many extremely powerful features, as you've seen so far, which require a balancing act between various features and your code. Combining those together while maintaining the required reliability and the performance that your application requires is quite a challenge, especially considering how much cycles need to be invested into maintaining an application that has business concerns and the messaging concerns. This is what we're going to cover during our next webinar in 2 weeks from now. How can we achieve what we want in possibly lighter and easier way.